So we are going to be recording this workshop, and if anybody would like to see the recording afterwards, just let me know. I'm also going to hit the live transcript. The automatic transcript. So you can hide that from your view if you find that distracting, which frankly I do. Today we're joined by Angel Ortiz. He's with the Center for EcoTechnology, and Angel is a real expert in energy management, energy audits, and I'm really very happy that he was able to join us, particularly because Angel's not feeling super well today. So we will all be super kind to you, Angel. But that said, I look forward to the conversation, and Angel's put together a very interactive and useful 2-hour workshop for us. So I'm very grateful that you're here, and I want to just invite you to take it away. You are on mute.
Okay, hello, can you hear me?
Yeah, thanks, Angel.
Great, fantastic. Hello, everybody. Thank you for coming. My name is Angel Ortiz. I am with the Center for EcoTechnology. I am a certified energy manager and a certified energy auditor through the Association of Energy Engineers. And I wanted to put together a brief introduction to energy management, what it is, what sorts of things you can be looking for in your facilities to facilitate energy efficiency and improved energy management where you are. So just a little bit about CET. We've been around for over 40 years. We are a nonprofit based in Western Massachusetts. Our motto is we help people and businesses save energy and reduce waste. And the tagline is we make green make sense. So we've worked in a lot of different fields, commercial energy, residential mass save, recycling works, commercial food waste. A lot of these things are very important for maintaining positive energy usage within facilities and within homes, and every little bit counts. So over the past few years, I've worked a lot on the commercial energy side of things. I will send a PDF of the presentation or through Pam afterwards. Apologies for not getting it sooner, but there's a little bit of transferring from PowerPoint to PDF, some of the notes and whatnot. I just want to make sure that they're presentable before sending it out. So in terms of some of the projects that I've worked on in the past few years, there's a little pie chart here. A lot of the work that we do is weatherization, so insulation of buildings, working on boilers and wrapping pipes, process pipes, domestic hot water pipes. We've worked with a lot of other projects such as DHW, which is domestic hot water, heat recovery, energy management system projects, controls, and a lot of steam traps. And I'll be getting into a lot of what these are as we move along in the presentation. And some of the companies that we've partnered with to perform the work are listed on screen. At Center for EcoTechnology, with the commercial side of things, we mostly work as a representative or an administrative force for the utilities. So we are able to scope out projects and then connect customers who have potential projects with vendors who are able to accomplish the work. The utilities offer a lot of great incentives for energy efficiency projects that I'll also be getting to in a little bit. So first and foremost, the question is, what is energy management? So energy management is described by the Association of Energy Engineers as the use of engineering and economic principles to control energy costs while providing needed services in buildings and industries. There are a few main components of what a good energy manager should do. First and foremost is understanding the energy usage of the facility. Being able to conduct energy surveys and determine where potential savings lie. create cost-effective improvements, so ensuring that the improvements that we offer or suggest are actually cost-efficient and make sense to pursue. And then most importantly, a good energy manager knows where to get additional help and knows whom to ask and where to go to actually accomplish work. In terms of generating energy savings, there is a bit of a hierarchy on what sorts of projects would do best. Most importantly is optimizing current energy use. So determining what sorts of things can be fixed without buying anything new. If it means changing from one energy source to another, such as changing from oil to electricity or oil to natural gas, that too could generate energy savings, and improving the energy efficiency of the entire system as a whole. Some of the benefits of energy improvement are, first and foremost, you're going to pay less for your energy bills, which is always nice. You also lower carbon dioxide emissions substantially in some cases. And with things like wrapping pipes, replacing steam traps, checking for leaks, you improve the safety and efficiency of your systems. So just a quick poll for people in attendance. What percentage of the energy produced in the United States is wasted? Be a poll with a few options. So of all the energy that is produced in the United States, how much do you think is wasted? Give everybody a moment to participate.
So we've got almost everybody.
I'm not sure if that's counting me and you as part of the participants. I'm not sure.
It may be. So I think you're right. And Mark shared his thought on that. So I'm going to end the poll and I'll share the results. So it looks
Great.
like most people think it's between the 25 and 50%. Mark also thinks he's in that range.
Yeah, that is a very good guess. In actuality, it's about 66, 67% of energy gets rejected. So you can see this is the estimated energy consumption of the United States in 2021. The Lawrence Livermore National Laboratory does this by state and by sector. You could see right here on the right, about 65 of that 97.3 quads is rejected energy. And in the industrial sector, a little over half of the 26 quads input is immediately rejected. So there is a lot of potential for energy efficiency in the industrial sector. You can see that a lot of the energy used for industrial comes from natural gas and petroleum, with a little bit coming from biomass and a little bit coming from coal. But most of the energy coming from natural gas is able to be saved through some of the methods we'll be talking about today. So some of the topics we'll consider today, and we'll spend about 30 minutes on each. First off, what is energy? When we talk about energy, what do we mean? Go a little bit into what an energy audit is and what it entails. And then we're going to talk about two of the larger topics, just do a little quick crash course into boilers and steam systems, as well as some industrial systems such as pumps and compressed air. So going into our first topic of energy. Energy is defined as the amount of work in physics that's force times distance or displacement that is done. The standard unit for energy in the United States is the British thermal unit, and it's going to be referred to as BTUs. 1 BTU is the amount of energy that's required to heat 1 pound of water 1 degree Fahrenheit. Power is another term that's used very frequently in conjunction with energy. Power is the measure for how fast work is done. So in other words, power is the rate at which energy is used. Power is equal to energy divided by the time required. So in our case, it's the British thermal unit per hour. And that's going to be shortened down to MBH, or 1,000 BTUs per hour. Electrical power is measured in watts, which is joules per second, because electricity needs to overcome resistance within the wire. So there's a little bit of a different metric used to describe electrical power. Given that information, what is the unit for electrical energy? Given that the unit for electrical power is measured in watts, what would the unit for electrical energy be? I have some options on the screen there.
All right, one more answer. There we go. All right, I'm going to end the poll and share the results. You'll notice, Angel, that I added one on there.
I did see that, yeah. I appreciate that. So the unit for electrical energy is the watt hour. Power is watts. Then if power is energy over time, then we multiply by time for both sides. So energy is equal to power times multiplied by time, which is watts times hour, so watt hour. Amperes is a unit for electrical current, which is similar but a little different in terms of rate of flow. Current is equal to the rate of flow, but measuring resistance as well. The standard is watt hours. So moving into just brief differentiation between energy or power, because they are just very often confused. The thing that I like to think about that's used often as an example is thinking of the odometer and the speedometer on your car. So energy is like the odometer in that it tells us how far we've driven, and power is like the speedometer that tells us how fast we're going. So when you have a lot of power, you measure how fast you've been going over a period of time and you get the distance. So very similarly, if you measure how much power you're using over time, that's the amount of energy you've used. There are some helpful energy conversion units. You don't need to know these off the top of your head, but a watt is equal to about 3.412 BTUs per hour. And then a kilowatt is 1,000 watts. Electrical horsepower is different from boiler horsepower. Electrical horsepower is 746 watts. And then in terms of natural gas, 1 cubic foot of natural gas, so a foot by a foot by a foot, is about 1,000 BTUs. And 1 CCF, you'll see that measurement a lot with natural gas, is 100 cubic feet of natural gas. 1 therm of natural gas is how the utilities measure your usage for the most part. Therms are what's on your natural gas bill, and that's equal to 100,000 BTUs, which you'll notice is the same as 1 CCF. So a CCF and a therm are interchangeable. And then 1 gallon of number 2 fuel oil, which is mostly what's used in industrial settings for oil, contains 140,000 BTUs. So that's a pretty cool set of numbers, but it's rather meaningless on its own. So as an example of how this is useful, how many MBTUs are in 10 gallons of number 2 fuel? Knowing that 1 gallon is equal to 140,000 BTUs.
Anybody want to unmute themselves, share your video, and let us know what you think? They're shy, Angel.
Okay, if not, yeah. So the way that we would do this is we would take the 10 gallons, and then we know that a gallon is equal to 140,000 BTUs. And we know that 1 MBTU is equal to 1,000 BTUs. So energy conversion is basically just canceling out units and getting to the unit you want. So we want to get to MBTUs and we have gallons. So we can cross out the gallons here. because it's a gallon over a gallon cancels out. And then over here as well, the BTUs cancel out, BTU over BTU. And then we can just knock out the 3 zeros here on the 140,000, 1,000. So we're left with 10 times 1,400. No, excuse me, 10 times 140, which is 1,400 MBTUs. A practical application of this is for point of use cost. So point of use cost depends on how expensive your energy is purchased for, as well as how efficiently the equipment makes use of the fuel. And in order to determine how fuels compare to each other, there is a common energy unit, which we sort of do the math to get all of the units to equal to. And by doing that, we're able to compare fuels to one another. And the common unit is the MMBTU, which is equal to 1,000,000 BTUs. So as an example, I'm just going to go through this one real quick. Let's say that a facility has a dual fuel steam boiler that you can operate either with natural gas or number 2 fuel oil. When you use natural gas and it's purchased at 142 per therm, which is the price of natural gas as of last month, the boiler is 80% efficient. Using oil at $4.70 per gallon, the boiler is 75% efficient. Which fuel source provides the lowest operating cost? I'm just going to go through this one real quick. So we know that a therm is equal to 100,000 BTUs and a gallon of oil is equal to 140,000 BTUs. By doing that same cross multiplication using the dollar per therm or the dollar per gallon and how much energy is in each of those, and multiplying by the inverse of the efficiency, because that amount gives you what you're actually inputting. The difference in these is how many therms you're inputting, basically. So the boiler running at 80% efficiency, you're going to need 1 divided by 0.8 as input for the same amount as the 1 divided by 0.75. So just doing that quick math, you could see that gas costs $17.75 for every MMBTU, and oil costs $44.76 for every MMBTU. So it's about, $27 more expensive per MMBTU for oil than for gas nowadays, given these efficiencies.
And that's
Sure.
those are MMBTUs delivered.
Yes.
Not in the supply.
Correct.
So
that's the purchase point.
Well, it's what it's costing you to deliver that many MMBTUs to the end use.
Correct. Yes.
Because the denominator isn't how many million BTUs you bought. It's how many. Well, actually, it's the per million BTUs used, because when you divide by the efficiency, right? Or am I missing that?
Repeat the question one more time. Sorry.
So because you're dividing by the efficiency, it's the number. It's the cost per million BTUs used
At the supply. Because if you were to multiply by the efficiency, that would be from input to output. So dividing by the efficiency, you go from output to input.
Right. So those are million BTUs per BTUs output. And that's
Correct.
the common basis between this comparison.
Yes.
Good, thanks.
Yeah. So just doing one more example, we're gonna split you into breakout rooms to do this real quick. So using those same numbers, let's calculate the point of use for a natural gas boiler running at 75% efficiency, a fuel oil running at 80% efficiency, and then this is the electricity price that I got that's most recent. So imagine you had an electric system that was running at an efficiency of 99%. How we would compare those points of use given these calculations.
So what I'm going to do before I break everybody into breakouts is ask you to jot down this information. because you won't see this slide when you go into the breakout room. And Angel, once I break them out into breakout rooms, maybe you can check in and make sure everybody has the information they need.
Sure.
Okay. All right. I'm gonna set you up into 3 different breakout rooms, and we'll give you 5 minutes to just work together and figure this out. Okay. Go ahead and join your breakout rooms and turn on your video. Walter and Carrie, you're going to join? Excellent.
There they go.
Okay.
Okay.
So it actually set you into a room, but that's okay. They can wait. Yeah. Because we can't share, they can't see the slide when we go into breakouts. It would be good if you could just pop into each room. Do you know how to do that?
Yeah. I'll join each of them and make sure that everybody's on their merry way.
Excellent. Thanks so much.
Yeah.
And I'll bring everybody back. Like, yeah. Resume recording. All right, fun. Everybody loves to do a little engineering calculations, right? Yay.
Yeah.
Yeah. That's what I thought. We have everybody back, so why don't we go ahead?
Yeah. So what did people have as the answer? I think it's pretty much the same for the gas and the oil, but for the electricity, what did we arrive at? Whoever, just go ahead, spitball.
Yep, feel free.
I got $41.45 per MMBTU.
All right, did the other groups get that? $41, $40.41, was that it?
I got $41.45.
$41.45.
What did the other groups get?
A very small number.
What'd you get? Well,
We did something very wrong, obviously.
okay, well, it's
I
okay.
got 482, but. I
Okay,
think
so we're orders of magnitude around the problem. That's fine. We can figure out what that is. Angel, you want to share your screen again?
Oh, am I not? Okay.
You are not. That's
Good to
okay.
know. Thank you. Share screen. Okay, so very similarly to how we did the previous example. So we have 0.14 over kilowatt, and then that's multiplied by 3,412. 1 kilowatt hour is over 3,412 BTUs.
Are you showing, can you show us the solution as you walk through that? Or
so we're going to be working through the solution because I kind of assumed everybody would get the same answer.
Okay.
So we're working through it together. So 0.14 over kWh multiplied by 1 kWh over 3,412 BTUs multiplied by 1 million BTUs over 1 MBTU multiplied by the efficiency, which is 1 divided by 0.99. Is anybody seeing where they went wrong now? Or
I'm not seeing your calculation on my screen.
yes, let me figure out how I can do that.
so 14 cents per kilowatt hours divided by
hold on, let me do this. That's going to stop sharing, hopefully.
Yeah.
So let me pull up the screen and share that. Share. So you should be able to see this now, right?
Yep.
All right, so if we insert an equation, it would be 0.14 divided by kilowatt hour
Mhm.
multiplied by 1 kilowatt hour is equal to 3,412 BTUs multiplied by 1 million BTU per 1 MMBTU multiplied by the efficiency, which is 1 divided by 0.99. So that equals 41.446 or 45 per MMBTU.
So do people see where they went wrong?
Yeah, I listened to you, Pam. You said 3.41 watts per BTU per hour, and it's 1 watt per the 3.41 BTUs per hour.
Yeah, so 1 kilowatt hour is 3,412 BTUs. That is the, if I were to go back a ways, yeah, 1 watt is equal to 3.412, and then 1 kilowatt is equal to 1,000 watts. So
you didn't really listen to me, Andy, because I said 1 watt equals.
yeah, and then watt hours, you multiply by the hours, and it cancels out the hours.
Sorry about that, Pam.
No, it's you throw me under the bus, that's fine. I'll just throw you back. Okay, great. Thank you.
Yeah, I completely thought that the this would still be visible when people were doing it. I apologize.
Okay.
Knowing for the next one, that'll be good. So we'll go back to the presentation. Let me stop my share real quick. Turn the animation back on. Share the presentation again. Let me know if everybody, nope, that's my view. Let me know if everybody can see this.
Yep, great.
Great. So there is a lot more that goes into energy management. This is a point of use comparison for boilers and fuels. A lot of other energy management requires similar calculations for different sorts of measures. So going from unwrapped pipe to wrapped pipe in terms of pipe insulation, you can know how much heat the pipe is expelling depending on the material it's made of, and how much it does depending on how much insulation there is. There are various tools to accomplish the tasks. Engineers are very big on creating tables and making things as seamless and quick as possible. So this was just one example for energy calculations. We're going to move into the next section, which is energy audits. Does anybody have any questions about anything we discussed so far?
I just want to check in with the other breakout room. So you saw where you went wrong, did you? That last calculation. So it's really just like any engineering calculation or any mass balance, you're paying attention to your units, and I find that 9 times out of 10 it's not paying attention to the units that leads to an error. Any other comments about what we did around what energy is and how you can calculate it? Nope, I think we're good, Angel.
Great. So I'm going to move into a brief description of energy audits, what we're talking about when we use the word energy audits and what's involved with an energy audit very briefly. So energy audit is a method of surveying a facility to identify unoptimized systems and identify energy saving opportunities. There is a hierarchy of projects. So when I would go on site for an energy audit, there are things that I would be looking for in terms of communicating with the customer or the facility, what's the most important to look at. So first and foremost is waste elimination. So fixing up your processes and determining where waste currently resides that can be fixed without major capital investment is definitely the most cost effective and the first thing that we look for. Low risk projects, so improving techniques, things that don't require a lot of changeover or lost production time are other things that we would mention near the top. Major conservation items are a little more work intensive than waste elimination or low risk projects. So we would definitely suggest these, but after the first two things are done, then lastly, the major capital improvement project. So things like replacing the boiler or putting in more efficient systems. We would want to see if there were opportunities that could be realized without investing capital, because that's when it becomes an issue where the financial department has to get involved, or the project needs to be pushed out depending on sometimes very rigid capital planning documents.
So Angel,
So,
before you move
sorry.
on, could
Sure.
you just go back? And I just want to ask folks, so when we look at this hierarchy of projects and we think about it in the context of toxic waste reduction planning, which is the reason why we're doing this workshop, is to see how we can be using our TUR planning techniques and applying them to resource conservation. Where are the similarities? What does waste elimination relate to in the TUR planning technique world?
Use per unit of product.
Yeah,
By
yeah,
eliminating waste, I improve my usage per unit of product.
yeah, yep, yep. So it's definitely an efficiency. And I'm thinking about what I'm thinking about right now are the different TUR techniques. So which of the TUR techniques is kind of like the first thing that you do that really gets you towards getting rid of waste?
Improved operation.
One of the things you're working on is accounting, right? You're looking at the cost.
Absolutely, Jim. And so, yeah, I mean, the whole process of toxic use reduction planning and resource conservation planning is making sure that you understand where the uses are, right? So I guess I'm asking the question a little bit awkwardly. I was thinking about the 6 different TUR techniques. And so maybe one of our newer planners can jump in and say what they think. And really look at any of these and you can see how they relate to a TUR planning technique. So Stephanie or Sarah in particular, if you're walking around the facility and looking for where there is waste, where there are things that can be changed to kind of quickly sort of get that low-hanging fruit and eliminate waste of energy use, how does that relate to toxic waste reduction planning techniques?
Input substitution. We're talking about that first one, waste elimination?
Yeah, it's, it's maybe not as obvious as it ought to be. And I think of operations and maintenance. So what are the low-hanging fruit typically with toxic waste reduction? It's walking around your facility and going, oh my gosh, if I put the bung on this drum, if I make sure that I'm not leaking, those are the things that can kind of quickly be done that get you to a more efficient process. When we think about the low risk projects that Angel has presented, these are improved techniques. So to me, that relates very closely to process modernization, adding things to your process, tweaking the process so that you can better control what you're doing. So in TUR, it's process modernization. Here we're looking at, other improved techniques that relate more towards energy, of course. And then the major conservation efforts and major capital improvement projects, those to me speak to the idea of process modification or redesign. So those are the really big process projects that require a lot of buy-in from your facility. So just like with TUR planning, there are different techniques that you can be applying. When we talk about input substitution, we'll be talking later on about, and we talked about it just a little bit ago, there's different fuel sources that you can be looking at with energy, and that's replacing one fuel source could be kind of with another, could be linked to or related to the input substitution. So I'm sorry to interrupt there, Angel. I just wanted to kind of get people thinking about what we're hearing here in terms of themselves as toxic use reduction planners.
Oh, definitely no problem at all. That's why we're here. So I'm glad that there is good overlap in the processes. So going into energy audits a little bit further, one of the first things that we do in an energy audit is identify the SEUs, or the significant energy users. What sorts of things on site are using the most energy, whether it be process, whether it be, most of the time it's the boiler or other mechanical or HVAC systems, but figuring out what's using the energy on site. Usually before I go on site, I'll look at the customer's energy bills, their recent energy usage, and determine if they're using a lot of energy all the time. So if they're using a lot of natural gas during summer, I assume that they're using natural gas mostly for production. If they have high winter usage and lower summer usage, then I assume that most of their natural gas is going towards space heating. Sometimes that isn't the case depending on production schedules, but noticing what's being done with the energy is very important, and usually the first step that happens before the energy audit. We then identify KPIs, key performance indicators. So what sorts of things are we looking for in terms of reduction? What percentages or amount lowering is acceptable for the customer? Would identify a good project. If it saves $10,000 a year but costs $100,000 to install or change over, then maybe we're looking for projects that have lower returns, lower periods to return on investment. Along with that, we're identifying all of the opportunities that are available on site and then quantifying them, and then taking all of this information and providing a roadmap for the client to figure out what would be the best use of their time and of their money, and what would have the least impact on site. So another poll question, there are going to be a couple of project types that Pam's going to send over. Which of these do you think provides, on average, the best return on investment?
All right, I've launched that poll.
I may have given away too much.
All that means, yep, I think you gave away too much. Why don't you go ahead and describe why that's the answer?
Great.
I'm going to share the results with you all. Look at you guys. All
Good job.
said the same thing.
So looking at typical returns on investment, so determining how quickly a project pays for itself. Equipment replacement usually has a return on investment of over 20%, but demand side management, so figuring out the demand and determining how to better manage what's actually being needed, that has usually over 50% return on investment, but energy conservation usually has over 100% return on investment. And
would you clarify what you mean by demand side management versus conservation?
Yeah, so demand side management is more determining what's necessary for usage and seeing if there are ways to reduce the actual usage, as opposed to conservation, which is taking the efficiencies of the objects or the systems and increasing efficiency. So they both basically result in a very similar reduction of things input, but demand side management is more like motor loads or compressed air pressures or
Time, wouldn't it also be
different
timing as
processes.
far as rates that are determined by peak loads?
On the electric side, yes. So thank you. So I definitely focus more on natural gas, I'll admit. So some of the electric things I'll be glossing over and I apologize. But for peak loads, summer load usage, determining when in the process things can be moved to in order to reduce the peak rate that you're paying, which doesn't happen as much for natural gas, but can in the wintertime. So determining when things can be used, how much needs to be used, and conservation is more reducing the not the load. It's increasing the efficiency of the system.
Yeah, because there's also demand, or should we say curtailment contracts that are going on now. And would you consider that TUR, that a company is getting paid to curtail its operations?
Is that a question for Pam? TUR?
Yeah, so if a company is getting paid to stop using during certain times, is that what you're saying, Andy?
Yeah, that market is growing out there. And I'm watching this happen, and people are saying, oh, we're doing, they're on their reduction kick, and they're bringing up these demand contracts, and it's like, okay, well, is that TUR? So I wanted to bring it up in this context. And when he said demand side management, it's like, well, is that TUR or not?
Is that going to be able to help a facility reduce its use of energy?
No. Well, it will overall, but also complementarily reduce its production.
Right. So just like with TUR, we do it based on production, right? So we normalize based on production. So whether you are reducing your production or not shouldn't affect your assessment of whether or not you've been able to reduce your use. So I think in that case, the answer would be no, Andy.
Right. Okay.
Does anybody have any question about that conversation there? Anybody want to add anything? Okay. Anything else, Andy?
I mean, it does have the aspect, I'll just bring in one aspect, which is that if the grid is running without when they're not on their peak, and when they pull on peak loads, the people that they're pulling in later on are going to likely have higher emissions.
That is true. It's because they supplement with, coal and
any variety of stuff.
Yeah.
How you get on the grid depends on a number of factors, how fast you get on, how much emissions you have, and their priorities and preferences. But as you go down the chain, you are typically going to have a little bit more offsite emissions. So your scope 2 concept is actually maybe improved, but for the grid, not for the facility itself.
Right. So I think that's a really important caveat there, that we're looking at the facility versus the overall use. And so again, not to say, it's like when we talk about chemical use and we talk about recycling that is not done in a way that's inherent to the process, it doesn't mean that recycling is not something you should be pursuing. It just means that it doesn't get counted as a toxic use reduction effort. So same thing here. reducing the load on the grid is something worth considering. Wouldn't necessarily be something that would be considered resource conservation under the Toxic Use Reduction Act. Okay, why don't we go
Good to
on?
know.
Thank you.
It's a great question. So looking into energy conservation generally includes waste minimization and maintenance, making sure that your occupied heating and cooling set points are always in effect, that any schedules for management systems, making sure that they're not overridden. If you have pipes that are transporting heat in any way, they should be insulated, making sure that your steam traps are functional. And I'm going to get into steam traps a bit later, but these are, some very quick, low cost ways of ensuring that your energy is being conserved as much as possible. So one of the standards for energy audits is the ISO 50001, globally applicable energy management standard that requires top management establish, implement, and maintain an energy policy and provide funding for projects. At its core, it's designed to help companies better use their energy consuming assets, evaluate and prioritize the implementation of energy efficiency technology, and promote efficiency throughout the supply chain. So the energy audit process goes from planning the energy audit, having a meeting with the facility or customer, or collecting data. So these two things happen sort of in tandem. Create a plan for how things are going to be measured, actually conduct the site visit, which will further inform how to better measure some of the things discovered on site, an analysis of the things found on site that are able to be more efficient, which again informs the plan for how to measure things. After this measurement and analysis is done, there is a report that's created from the energy audit that details the savings measures, which is presented at a closing meeting. So this is the standard process by which energy audits happen.
What sort of time frame is involved?
It really depends on what type of energy audit we're doing. So there are a couple of different levels of energy audits that I'll be getting into. For the base one, we're talking about a couple of hours on site to look at some of the bigger ticket items, some of the conservation measures that are more easily seen. If we're looking at things like figuring out what schedules are no longer serving the function, for instance, if thermostats were put into a room and then the room was the walls were broken and it's actually two rooms, but there's only still one thermostat that's not designed for the space. That sort of retro commissioning work does require weeks of data being measured. For examples like thermostatic reset valves on radiators not functioning well, we may put in space heat data loggers for 3 weeks, a month to determine how much the spaces are being overheated. So it really depends on what sorts of items we're looking at, but it could be, a couple of hours to a couple of weeks of data necessary. Usually for steam traps, which are a bigger item that we work on, the survey, they can do about 50 to 60 traps a day. So if your facility has 200 traps or something, that's like a 3 to 4 day study. So it's really dependent on the level of audit and the sorts of objects we're looking at. So looking at, of course, looking at the different types of audits, there's a simple facility audit, which is known as the level 1 energy audit. There's a detailed feasibility study or a complex facility study, known as the level 2 energy audit. And then the advanced feasibility study is known as a level 3 energy audit. So you can see this graph shows the range of accuracy of estimates. For a level 1 audit, we're pretty ballparking some of the estimates. So the cost accuracy is about 40 to 50%. For a lot of those measures, we're looking at previous comparable facilities with comparable projects and how much they've saved, and basing estimates off of that. With the feasibility study and a more in-depth engineering study, we get that accuracy a little closer. And then with a level 3 study with computer simulation, we're pretty honed in on the actual cost of the measures. And then a lot of the engineering studies require measurement and verification, or M&V. The utilities will require that to ensure that the savings that were reported are actually being realized. So the more time and energy you're willing to put into the audit, the better estimates of savings you'll get. A lot of these higher level studies require an engineering firm to do the calculations, because we're talking some more complex systems, but the utilities do have offerings to help ease the financial burden for facilities. So they'll pay a portion of the cost of the engineering study. So getting into a bit more detail on each of the levels, the walkthrough, or the ASHRAE level 1 audit, is a site visit with personnel on site to gather data. While on site, we'll be able to identify operation and maintenance issues, identify low-cost energy efficiency measures such as wrapping pipes or replacing non-low-flow water fixtures with low-flow water fixtures, which is something that can be done relatively quickly and easily. And we include rough estimates for returns on investment. And during this, we will identify larger capital projects that do require more study to fully flush out. Analysis, or an ASHRAE level 2 audit, reviews the operation and maintenance procedures more qualitatively, more in depth, determining where in the actual processes that exist there is room for improvement. This is where we would be looking at data loggers, or asking the people who are in charge of creating the schedules to send them over and look at what the sensors indicate. We'll be collecting more data and taking more measurements, and at the end of it, providing an engineering study to produce more detailed savings and cost analysis. And there will still be some capital intensive improvements that require further study that would not be covered by this audit. A computer simulation, or ASHRAE level 3 audit, requires detailed and time intensive field data gathering. This is where we're looking at weeks or months of data gathering during heating season, during peak loads, if the savings are electrical, to determine what energy is being used and when. This does provide very detailed project cost and savings information to the highest degree of accuracy possible. And computer simulation is provided for hourly analysis of energy usage and impacts. And then there is the presentation of high, low, and most likely case assumptions. The utility offerings for these are that your utility does provide no-cost energy assessments for facilities. So the level 1 walkthroughs are something that, especially in Massachusetts, I'm not sure everybody is, but a lot of this is, in my experience, Massachusetts-based. Through the Commercial Industrial Mass Safe program, level 1 ASHRAE walkthroughs are offered at no cost for rate users. Engineering studies, when necessitated, are also incentivized, usually at 50-50. So what that means is that the utility will provide 50% of the cost of the study before the study is done, and the other 50% after the work is completed. So at the end of the day, you'll have the work done and the study will have cost you nothing, but they keep that last 50% until the work is done to ensure that the work actually gets done. Depending on the size of the engineering study, sometimes they'll incentivize it based on predicted cost savings and not at the 50-50. And at CET, we provide ASHRAE level 1 audits to facilities. So that's it for
Angel, do you have a
Yeah.
particular size to the facility that you will come to in terms of their energy usage minimum that?
we work with anybody who has a commercial rate code in Massachusetts. So if you use gas and have a commercial rate code, we'd be able to visit you and talk to you. There's definitely, depending on the utility, it's sort of like a checkerboard in the same way that the utilities are checkerboard in Massachusetts. Different utilities have different vendors that they use for different regions. For Eversource, Liberty, and Berkshire Gas, to the best of my knowledge, we can do commercial industrial customers of any size.
Okay. How long are you booked out in terms of being able to get an audit done at a facility? Or maybe we can touch base afterwards.
We could touch base afterwards. Yes.
Okay.
I mean, it depends on where you are because we have auditors all over the state. So
Okay.
I don't do the scheduling, thank God. So
Thank you.
we'll talk at a later time. Yeah. Any other questions about energy audits?
I wonder if anyone on the call on this Zoom meeting has done an energy audit, either on your own or brought somebody in.
Yes.
You have?
Yes.
And I've done it both with bringing people in and doing the audit myself.
Yeah, that was the largest use of energy at the facility that I'm at is actually compressed air.
Mm-hmm.
So compressed air and basically dust collectors. So we've had energy audits on both.
And you were able to find efficiencies.
We've been able to find plenty of efficiencies. It's just a matter of reacting to every single one. There's quite a few that need to be handled. So you got to, like Angel said earlier, take the lowest hanging fruit.
Yeah,
That one
that's
first and kind of work your way back. And there are a lot of rebates out there, especially on the compressed air side.
yeah. Compressed air is a huge one. I go into a little bit of detail later on, not as much as it deserves, but compressed air is very similar to steam traps in that there's always going to be something at some point. So it's a matter of catching it quickly.
Great.
Great. So it is now 2
It is
p.m.
6, yeah.
We're about halfway. Great. So I'm going to go through a couple of these boiler and steam systems and then industrial system sections. Feel free to stop me if you have any questions. There's a lot of material to cover, so I'm going to be doing as much justice as I can to them, but I definitely won't be getting into the weeds as much as is necessary for something. So please bear with me for that. So boilers, most of your facilities, if not all of them, have them. Boilers are great. Some of the benefits of boilers are that they use water as a medium for heat exchange. Water and steam have very good heat transfer properties. Water is in this region widely available and low cost, and clean, non-toxic, generally safe, and very importantly, it has a very good ability to control pressure and temperature. So boilers are mostly used for heating and process because of how great of a medium water is. There are a couple of different kinds of boilers. So fire tube boilers are named that because fire goes through the tubes and the water is heated around the tubes. There are water tube boilers where the fire goes around the tubes and the water goes in the tubes. Water tube boilers are more used for larger boiler systems, and fire tubes are mainly used for small to medium-sized boilers. I believe that's based on the amount of water necessary to be pumped through the system. It is more cost-effective to keep them in the tubes within the boiler at larger sizes. So in terms of sizing boilers, boilers are sized based on their input and their output. Their input rate is measured in MMBTUs per hour, or MBH, which is MBTUs per hour. Boiler output rate is measured in horsepower, and 1 boiler horsepower is equal to 33,475 BTUs per hour, completely different from electrical horsepower. You'd have to ask an engineer about that. Horsepower. So I'm not going to make you go into breakout rooms again. Don't worry. If a boiler is 80% efficient and uses natural gas at a rate of 10 MMBTUs per hour, what is its horsepower? Well, we can get that by taking the efficiency, taking the MMBTUs per hour, and then knowing that 1 horsepower is equal to 33,475 BTUs per hour. The hour bounces out here and then cancels out, and then the BTUs cancel out. So we're just left with horsepower, and that equals 239 horsepower. So a quick question, what is the relationship between efficiency, input, and horsepower? So looking at this, we can see, does anybody have a guess as to this? What is the relationship between efficiency, input, and horsepower?
Direct relationship.
Yes, yes. So as efficiency increases or as input increases, your horsepower increases. So increasing the efficiency of your boiler results in more horsepower. There we go. So combustion, boilers work through the process of combustion, which is the chemical reaction by which heat is created and released. Fuels get their energy production potential from hydrocarbons, which are molecules that contain carbon and hydrogen. In an ideal reaction, where there is exactly enough air to react with all the fuel, we get this fun equation, CH4 plus oxygen plus nitrogen, which is air, so fuel and air, combine and give us carbon dioxide, water, nitrogen, and energy. In reality, because there is always excess air in the reaction, there is always excess oxygen exhausted out of the boiler. The 3 T's of optimal combustion are time, temperature, and turbulence, so how much mixing there is going on. And in an actual real world situation, because there is an excess of air, we see that this results in carbon dioxide, water, nitrogen, and heat, but also excess air and some NOx and SOx, which are dangerous chemicals that we would like to reduce as much as possible. So in terms of increasing boiler efficiency, you're also reducing the amount of hazardous chemicals that are being released. Exhausted heat and excess air are 2 metrics by which boiler inefficiency can be measured. As a rule of thumb, boiler efficiency increases by 1% for each 40 degrees Fahrenheit reduction in stack gas temperature or 15% reduction in excess air. And because it's a lot easier to look at tables and calculate everything as you go, there are some combustion efficiency tables for different fuel types that are available. I'm going to give an example of one. It's a lot less scary than it looks. So the stack temperature rise is the how much heat is being lost through the exhaust of the boiler. And then you can measure the amount of excess oxygen. They make these testo wands that you could put into the exhaust of a boiler that will measure the temperature of the air as well as the excess oxygen and carbon dioxide. So we can see that given, for instance, a stack temperature rise of 250 degrees and an excess oxygen level of 8.5, it's running at 82% efficiency. So as the stack temperature rise decreases or as the oxygen increases, the efficiencies get higher and higher. So doing some of these savings calculations, we're going to use that previous example. Let's say you have a gas-fired boiler with an input of 10 MMBTU per hour that currently measures 310 degrees stack temperature rise and 11% excess oxygen. You do some maintenance on it, you bring a boiler person in, and they're able to reduce the stack temperature rise to 200 degrees and the excess oxygen to 2%. How much money are you now saving? I think we're just going to go through this one in the interest of time. So looking at those numbers, so the 310 stack temperature rise, 11% excess air, going to 200 stack temperature rise and 2% excess oxygen. We would find that first number at 310 and 11, which gives us that 78. And then look at where it went. So it went to 200 and 2% excess oxygen. So it went to 85.4. So looking at those numbers with the $1.42 per therm, we went from 78% efficiency to 85.4% efficiency. So the amount of money being spent per hour is about $15.77 per hour in savings, which, you know, if you have a boiler that runs 16 hours a day, 6 days a week, that's about $78,750 a year that you're saving. So sometimes that boiler maintenance, if it hasn't been done for a while and we can reduce those major inefficiencies, can result in some very drastic savings over the long run.
Don't we have regulatory requirements for tune-ups based on the size of boilers too?
Those
By
do
regulation?
Yes. And, you know, sometimes those, I'm actually not in a facility, so I don't know if those get delayed, but I've definitely seen some boilers in smaller facilities that have not been serviced in a long time, or boilers that if you do the bare minimum, as opposed to some of the things that we're going to be looking at in terms of how to decrease that stack temperature rise, these are some of the things that could be realized. I'm sure that there are things that are mandated. And it's also good to know that you are doing those things that are mandated and looking at the numbers from before and after, determining just how more efficiently the boiler is running because of those. These are ways to quantify that. So how to reduce the stack temperature rise? Number one is cleaning the heat transfer surface, installing sensible heat recovery. You can preheat the incoming combustion air. And if you have condensing boilers, you can ensure that they are actually condensing. So in terms of condensing boilers, they utilize condensing economizers. And the way that they work is they extract the available latent heat of the water vapor in the exhaust. However, due to the low exhaust temperature that's required for condensing to actually occur, the incoming water must be under 100 degrees Fahrenheit in order to recover the heat, and heat cannot be condensed if the incoming water is 130 degrees Fahrenheit or higher. So it is important with condensing boilers to make sure that these parameters are met so that they're actually condensing. I've been to too many facilities to count that the condensing boilers are set up in a way that they're not actually condensing, and at which point they're running at a standard efficiency. So I know that a lot of places, when they're doing facilities capital planning, looking at these condensing boilers that have rated efficiencies of 96, 97% efficiency, they have to be maintained in a very specific way in order for them to actually hit those numbers. I don't know if any of you have condensing boilers in your facility, but determining that they're actually condensing is something that a licensed boiler technician should be able to do. So moving into steam boilers, I have a little diagram of a steam system thanks to Armstrong. So there are a variety of different pressures that steam usually runs at for systems that require high pressure for large scale manufacturing and production. High pressure, we're talking anything north of 50 to 100 PSI. Low pressure steam is mostly for lower capacity manufacturing equipment or heating radiators. A lot of colleges run low pressure steam in a loop throughout the different buildings, the different dormitories. That's usually running at anywhere from 5 to 20 PSI. The higher the pressure of the steam is, the more temperature, the higher the temperature of the steam is. And you'll notice that this is going from the boiler to these different systems where its heat is being used by the system. And then as the heat of the steam is being used, it condensates and turns into water. This water is captured by steam traps and put back into the deaerator tank, where it is the oxygen and other gases such as carbon dioxide are removed, and then it's fed back into the boiler. When steam traps are not working, this condensate can go into the mechanicals, and because it's being pushed at a relatively high pressure because of the steam, it can cause damage to the pipes. It could cause damage to the mechanicals. And steam traps are one of those things that will always fail over a period of time. So it is important to get steam traps checked at the least every 5 years. If you can do it on a 2-year schedule, that's usually better. But when the traps aren't working, depending on what kind of trap they are, they'll either let condensate through into the system where it can cause damage, or it'll fail the other way and let dry steam out, which also reduces the efficiency of your system. So as you can see in this diagram, a lot of these little arrows are heat escaping the system. That's where pipe insulation comes in very handy, because especially with steam, the temperature differential between the air and the steam in the pipes is so great that a lot of that heat is being lost. Like the higher the temperature differential, the quicker the temperature tries to reach homeostasis, and the more heat you're losing out of your system. So high pressure steam pipes are very important to wrap because you're losing a lot of heat, and ensuring that there's insulation on those, keeping the heat in the system, means that you'll have less condensate happening, which means less damage to the machines and less damage to your pipes. And it also means that more heat is going where it needs to go. So also improving the efficiency of your system very much. I see very high returns on investment on steam pipe in particular because of how hot it usually runs. So that's basically steam boilers in a nutshell. Steam traps remove condensate to prevent water hammering and equipment damage. And as I mentioned, they remove gases such as air and carbon dioxide that don't condense. They fail, open, or close. So when they break, they either break open or they break closed, depending on what kind of trap it is. If they fail closed, then they're not removing condensate. And if they fail open, they're passing live steam or dry steam. So have a couple of pictures of steam traps. So you can see this is a free float steam trap. The steam comes into the system, and then the valve opens and lets the condensate through. And then this is the inverted bucket, which is another common kind of trap. It uses the buoyancy of this as condensate forms to operate this lever, which then allows the condensate to come out. So this is a picture of a steam trap. There are a lot of different kinds of steam traps, depending on the type of system that they're being used for. This is one of them that is done by American Plant Maintenance. They're one of the larger steam trap repair companies in this region. They're steam trap systems. There are a few other great ones, but they'll usually just leave these numbering tags in order to be able to better speak about them, so you know when they give their reports where the traps are, which traps are failing, which traps need to be repaired. One of the other great things that you can do with steam traps that I don't mention is because they need to be checked regularly, and they will leak if they're breaking sometimes. You can't put permanent insulation on them because you need to get to them at some point to replace them. So there are companies that make removable steam trap jackets. So basically I used to have one in my office, a little Velcro box that you can put on the steam trap that provides it insulation, but also is removable so that when it does need to be replaced or maneuvered in any way, it's easily accessible. They make those for valves, flanges, down stems as well. So removable insulation is definitely another often overlooked energy efficiency measure that I'll scope out at a lot of places, because a lot of places have steam traps and don't really see that as a permanent installation, but it is bare metal that is releasing heat. So we want to wrap as much bare metal as possible that's releasing heat when we're on site. Here are some infrared pictures of working steam traps. So you'll see that this is the inlet where the steam is coming in, and this is the outlet where the condensate is leaving. So you can see that the steam and the heat is passing through this trap and going to where it needs to go without issue. And the condensate, which is much cooler than steam because it's water, is leaving the system going to the condensate. In a failed trap, looking at it through an infrared camera, it would look a little more similar to this, but the entire trap would be the same color basically, which shows that the steam is leaving the system. So these are two different kinds of traps that show, if you have an infrared camera, great. I don't expect that many of you do, but it is a very common tool for energy auditors to determine whether a trap is functional or not. So that's basic rundown of boilers and steam systems. I know I flew by some stuff, so if you have any questions, please let me know.
So I wonder how many facilities have boilers and what kinds? If you wouldn't mind just sharing with the group. What about you, Jim? Do you guys have boilers on site?
Actually, we don't. We have the Modine heaters throughout the building, but no boilers because we're not doing any type of processing with, heating material.
Mm-hmm. And oh, it looks like Stephanie is not with us anymore. So Sarah, you say your clients have a ton of different types of boilers. And I'm sure that as consultants, you definitely see that a lot.
Hi Pam, this is
Oh, there
Stephanie.
you
I'm here. I was gonna say we have, I think, 11 or 12 natural gas boilers just at our Andover facility.
Yeah, yeah, I imagine so. I'm sorry, I was probably looking right at you and didn't see you. So, great. So this is, I think, very useful, Angel, and I really, the whole issue of steam traps and, how important it is to have those functioning well is an important thing to think about from a process perspective. So, very helpful.
Yeah, I would say it's helpful, like, just as a consultant, sometimes we'll get on site and the boiler is much older than anyone's tenure there. So it's kind of helpful to see some of these pictures and kind of some of the figures that you showed up to. So at least I can identify some parts of it, even if nobody knows where it came from or what it is.
Yeah, I remember I started in residential, and it was I had trained on a few different kinds of boilers and furnaces for houses, and I went to, I think it was like my first day, I went to a place and they had a really old like HB Smith steam boiler, and I took a picture. It's like I have no idea what I'm looking at. Like somebody please help me. And it's a lot of the older models aren't. They were package built and they were put in like section by section, and there's not a nameplate to speak of. So it's knowing how the boilers work, and sort of knowing what sorts of things they have in common, regardless of age or capacity. Hopefully, is helpful in sort of easing some of those questions. Definitely, a lot of additional information could be talked about, controls and burners, and improving efficiency in other ways, but I just wanted to give a little bit of a brief overlook on boilers.
Yeah, Angel, you brought up a good reminder, which is the tube cleaning.
Mhm.
And do you have any way of doing that without necessarily just taking the boiler down for inspection?
I do not personally know.
Okay.
That's a question for a boiler specialist.
Okay.
I apologize.
Oh. Wish you had the silver bullet.
Yeah, and it is difficult because a lot of these measures, energy efficiency measures, are necessitate just stopping production for a bit. So it's important to determine which ones don't, and determine which ones are more painless, and look at those.
I worked with a client that had a steam boiler at one point, and we actually went in to do an energy audit there and ended up focusing just on their boiler and their steam system, because they didn't want to put a lot of money into the whole process.
Mhm.
And we found a lot of low-hanging fruit there.
That's always a great feeling. I was at a hospital, that your question reminded me, I was at a hospital not too long ago, and they had high pressure going through the systems. And this gentleman was telling me that they had a steam leak, and the company that they used to replace, like a flange broke or something, but they had this like special foam that they put on the system that allowed them to like remove it and replace it without having to shut down. Which I had never heard of before, but it is very interesting because especially with the larger steam systems, it is something goes wrong on the high pressure line, you have to shut down everything. But apparently there are ways nowadays to be able to deal with it piecemeal. I haven't gotten more specifics about it, but there is a lot of technology that's been going on in looking at these systems and ensuring as little downtime as possible.
Angel, the other thing from experience was dealing with an old steam system. The more you keep it in tune and keep your your steam traps clean, the less chemical you use to treat the water, because those chemicals are getting very, very expensive now. And a lot of people forget about the chemical use in the systems.
It's very good to note. Thank you. Add that for next time. That's a that's a good plus. Great. So we're going to move into the next and final section on industrial systems. And I'm going to be going into a couple of things in, again, not as much detail as I would like, but here we go. So we're going to be talking about pumps very quickly. A lot of facilities have pumps for various usages, but most of the time they're oversized for the intended job and difficult to manage well. So one of the things that we recommend is installing a variable frequency drive, VFD, that allows for savings to be had by throttling the power to adequately address the amount of flow. So if you know that your pump is throttling and you can hear it, or you have measurements on the amount of flow and you know that it's throttling, installing a VFD to sort of match that does save a lot of electricity because you're only going to be using what you need for the appropriate time. So in terms of pump equations, I'm going to run through this one as well.
Can I ask a question?
Sure, please.
What does throttling mean?
Throttling is when the can hear it like if it sounds like your pump is like pumping gravel at times, or it's not a consistent flow, like you hear banging, or just know that it's operating at different flows depending on the day. That's throttling.
Isn't it just that you're restricting the flow with a valve and that's throttling?
Not as I understand it. That, maybe I'm thinking of a different definition.
So yeah, I always think of throttling as adjusting the flow, like doing like purposefully. But what you just described, Angel, I wondered if that was like cavitation, where you can get air.
Exactly.
That's okay. You didn't know, you're completely right. I apologize. That is cavitation.
Which is from a restricted or throttled inlet on the pump more often than not.
Right.
So I apologize.
Don't apologize. It's a good conversation.
Yeah, I thought that throttling is something that can occur. Like I know that you can throttle a pump, but throttling is also something that occurs if there's if it's oversized, like something that happens because the pump is oversized.
It may.
Am I wrong? Am I wrong in that? I understand that throttling is something that's done.
Let me do a little research while we continue on, and I'll see.
Okay. Again, I mostly work on natural gas. I apologize for some of the electrical things that are maybe lacking in detail. Interesting. So brake horsepower for pumps is equal to the pressure times the flow, which is the head, which is the distance between where it needs to go and where it goes underneath, and adding those to the static head and suction head, multiplied by the gallons per minute, divided by 3960, which is a constant used in the United States that I don't know all the details of, but I know the 3960 is a constant.
It's a constant for units of head in feet.
Okay, thank you. And then also by the pump efficiency. So in order to optimize pumps, you can use smaller pumps so that the unneeded capacity can be switched off. So switching from one large pump to multiple smaller pumps. If you hear a noise like the pump is pumping gravel, cavitation, raise the suction liquid level or lower the pump. And reduce pipe resistance by checking losses at valves, elbows, and strainers, and determine what is providing increased resistance. So this last one may require some more fundamental equipment rearrangement, but that pipe resistance also can decrease the efficiency of the pump. All right, so that's pumps. Compressed air. Compressed air systems are used for pneumatic tools, conveyors, packaging, and a lot of different types of production equipment. Compressed air is non-flammable and high torque, and most systems are about 20 to 25% efficient, so seek substitutes when possible. Obviously, compressed air is great at what it does. So for certain cases, it's not possible to seek substitutes, but there are some use cases where compressed air can be reduced or replaced with something else. So there are different kinds of compressed air systems. Reciprocating compressed air, usually smaller than 15 horsepower. They can handle pressures up to 50 psi, and they're used for small buildings and controls. There are rotary screw systems that usually about 5 to 500 horsepower, 25 to 150 psi, and are used for small to medium scale manufacturing. They have medium flow to them. And then if you require a system at higher pressure or capacity or need a higher flow, this is not compressed air. This is a centrifugal system. Runs through from 125 to 5,000 horsepower, 125 to 10,000 psi, and is used for larger manufacturing purposes. Compressed air systems require a lot of electricity to keep the air dry and flowing. So this is a cutaway of a desiccant dryer that removes some of the moisture in the air. It's very important that the compressed air remain as dry as possible. And so the moist air is exhausted through this into the atmosphere at the end. It passes through a desiccant, and the moisture is removed through absorption, and then there is some purge air passed as well, which regenerates the air. So this system does require electricity to remove the air, and then also, compressing the air requires a lot of electricity as well. There are receiver tanks that are part of compressed air systems that function like shock absorbers and act as a buffer for the pressure. They prevent the cycling of load or unload compressors by buffering for the pressure. And you can see these in a lot of various places. If they're wet, then they're located before the dryer. If they're dry, then they're after the dryer. They could be, depending on how large the plant is, located throughout the plant and at equipment that requires large loads. So you'll usually see a few of these in compressed air systems. In terms of saving energy, there are a few steps that we will go through in descending order. So number one is eliminating compressed air needs. Number two is fixing compressed air leaks. Then reducing excess pressure, improving controls, intaking outside air and rejecting waste heat, and finally replacing equipment. So I'm going to go through all of these briefly. So in terms of reducing your usage, poor usages of compressed air can be substituted with more energy efficient options. So if you are using compressed air for drying things or open blowing, finding other ways of drying things, or using engineered nozzles that have a very defined and low amount of pressure necessitated to dry things, sort of like a spray valve for washing dishes. Using those can reduce your compressed air usage. If you're using compressed air to aerate a liquid as part of a process, there are low pressure blowers, or using a mixer instead that would allow you to reduce the amount of compressed air needed. And then compressed air is sometimes used for air motors, and then replacing those with electric motors if possible, if it's safe. Air motors are put into place in situations where electric motors shouldn't be used for safety concerns for the most part, but if you do have air motors in places where electric motors can suffice, then replacing it with electric motors is a lot more efficient. Looking at compressed air leaks. So this is from a book entitled Maintenance Outperforms Wall Street by 10 times, which was a great conversation starter in the energy efficiency world. We can see that depending on the size of the hole of the leak, the amount of energy lost increases drastically. So usually my understanding of how they do compressed air leak surveys is just going through the system and using a foaming liquid to determine where the leaks are and then determining how large they are. But at 14 cents a kilowatt hour, if you have a small compressed air system at 5 psi, you have a couple of 3 millimeter holes in it, that's hundreds of dollars you're losing every year just for having a few leaks in the system. So making sure that you're getting your compressed air system surveyed regularly to avoid leaks and repair them when they pop up is definitely one of the highest return on investment measures for compressed air. In terms of reducing pressure and making sure that you have adequate pressure, first and foremost, you want to determine what your need actually is, what pressure is needed to operate plant tools, and make that pressure and not higher than that pressure. If you have a significant user of compressed air that uses a lot more than the other systems in the facility, then you can isolate that system if it absolutely requires a higher pressure and use smaller dedicated compressors for that, because you're reducing the amount of pressure you're making overall and you're reducing the size of the system, so reducing the chance for leaks. Each 2 psi of pressure reduction reduces compressor energy consumption by 1%. So if you have something that requires 40 psi and going, the rest of your system only requires 10, then that's a massive amount of energy that you're saving, about 50%. In terms of maintenance, making sure to clean the filters is very important. Clean your intake filters. Minimize unnecessary discharges by ensuring that you have adequate pressure throughout the system and that the system is set up in a way that you're not creating opportunities for discharges. Investigate those strategies and determine start-stop, the load-unload, and how the compressors are sequenced to see if there's any more efficient options. Maybe you've added things to the facility but kept the same compressor system in the same sequencing, or added one. Depending on when the system was initially put in and where your facility is now, it may not be the most efficient system for what you currently have. So taking a look at that, retro-commissioning the system ensures that you're getting the most efficiency out of that. And you can program a pressure setback during times the air isn't needed. So if you have one system that uses it, knowing when that thing is in production and setting a schedule to do a setback during times you don't need it also saves a lot of energy. This is based on 70-degree Fahrenheit intake temperature air. If you relocate the air intakes to cooler positions, you can save a substantial amount of energy power. The warmer the intake temperature is, the harder the compressors have to work and the more energy you use. So using outside air during the winter time, if you, I don't want to say because I haven't done this yet, but if you use refrigeration, potentially using that lower intake temperature could potentially be good. I'm thinking of waste heat in reverse, but maybe that doesn't work. And then speaking of waste heat, 85 to 90% of compressor input energy is lost as heat. So a fully loaded 100 horsepower compressor generates about 250 MBH, which is about 14 of those little Resnor space heaters. So for each horsepower of your compressor, assume that you have 2,500 BTUs per hour available to recover as heat. And then moving into waste heat recovery more holistically, waste heat is almost always all around you in an industrial facility. Things produce heat in a facility. And in order to harvest that heat, because we don't want it to be wasted, the waste heat needs to be high quality heat. It needs to be near a location where it can be reused. And it also needs to be created when it can be used elsewhere. So if you're using the heat and there's great places where it could go, but they're not happening at the same time, then storing that heat isn't necessarily efficient. Some of the waste heat sources that are common throughout facilities are the combustion flue gas, so that stack temperature rise we talked about earlier, lost condensate, the heat of the compression from compressors, waste combustibles like an RTO, or condensing water as part of a system of refrigeration. Some of the uses for this waste heat is to preheat combustion air or boiler feed water. So the boiler has to work less to bring the water to temperature. Preheating process flow if you're using machines or other systems that require a certain heat threshold, preheating that heat so that those machines have to work less. Space heating, or heating your domestic hot water. I have an example of an air-to-air heat exchanger. So see that the combustion system, fires, the heat goes into the system where it needs to go, and then this heat escapes out of the flue. With an air intake, you can install an air-to-air heat exchanger, which will capture some of this heat that's leaving and use it to preheat the air going into the boiler. So the boiler has to work less, so you save energy that way.
I wonder if
That-
anyone else.
That's actually pretty substantial. We did a drying oven and we reduced our gas usage by 50% with the air-to-air heat
50.
exchange. 50%.
Wow.
Now, what we did is we ran it year round, and in the wintertime, we actually upped our usage, our recovery by, we would feed it to the ends of the ovens as far as this, where it was being sucked in. And we'd also feed it into the building and replace building heat where the amount of exhaust was reduced as well, because we weren't running the other boilers, the other fired units.
That's an incredible amount of savings. That's great.
Yeah, I was just wondering if other people had examples of using the waste heat like that. That seems to me to be a real opportunity in production operations. I don't know, Jean, if you guys have had any success with that in your facility. It's okay.
In our
Anyway.
case, it was actually, we recovered that much heat, and it also was that we had to do pollution control on that hot air stream. And the cost of our control system actually was reduced by 50%. So the energy savings we had paid for the entire pollution control system in 3 years.
That's amazing. Those are the the gems I love to hear about. Heat recovery is one of those things that it's you gotta look for it in order to find it. It's not one of those unless it's very obvious. It is one of those things that requires an understanding of how the system works as a unit and determining where it can go. And a lot of them are larger scale capital projects, but sometimes there are examples where there's a lot of heat being used and immediately being ejected out of the building, and being able to do something with that is always fantastic. So it's really good to hear.
It seems to me that having the maintenance staff or having the process engineers with you as you walk through this kind of, looking for this kind of opportunity would be really important.
Yeah, definitely. And this heat recovery is always, how do I put it, a sort of a pie in the sky measure for a lot of people, because it comes after a lot of more low-hanging fruit, which also, improves the efficiency of the system, and allows for heat recovery to better be utilized. So it goes in tandem with a lot of the other energy efficiency measures spoken about previously.
There's also some interesting misconceptions about energy recovery, in that I've gone through facilities where it's just really hot, and you're dealing with worker safety in terms of heat indexes, and you bring up heat recovery and they're like, heat recovery, we don't want any more heat. We got too much. And the point is, it's about the containment of the heat, the recovery of the heat, and that the presence of that much heat in the workplace is a prime indicator that there's ample opportunity for recovery.
Yeah, definitely. I love going on a site and just, there's a maze of standing fans in the boiler room that are just blowing the air because it gets too hot without it. And it's, heat recovery can be used for a lot of different types of things, like space heating is just one of them, and improving the efficiency of the systems, especially with some higher heat thresholds, is a lot better. So yeah, definitely something to just keep an eye out if there are opportunities at your facilities, because most facilities will have an opportunity for waste heat recovery.
Another one is drying and drying ovens, that moisture content analysis and control can save huge amounts of energy. So one is, you're not over drying your product, you're not putting too much energy in. We saw some really substantial savings for a couple of clients, 10 to 15% energy usage reductions with just moisture monitoring.
It's always great. And then just have a quick example of a heat pump where outdoor air getting passed through, either if you have a mini split, you're taking heat from the outside and putting it in, or taking heat from the inside and pushing it out. And it's a lot more efficient than creating heat, because it's not creating heat, it's moving heat. And so you'll usually get efficiencies of over 100% with the heat pump, because for 1 kilowatt hour used, you're getting more energy out of it. The colder it is outside, the less efficiently they run, but some heat pumps nowadays that are rated for cold, they'll work up till like -10 degrees Fahrenheit at a pretty high efficiency. So heat pumps are another amazing technology that the utilities are, especially now with an increased push for electrification, are trying to push people towards more and more. So I'm going to go into a couple of projects.
Can I ask a question? Because you
Sure.
show a heat pump where you're exchanging energy from incoming air to outgoing air. What about enthalpy wheels, which are much more passive and don't involve the energy investment of a heat pump?
What about enthalpy wheels?
Well, enthalpy wheels they transfer the enthalpy from an incoming airstream and put it in the outgoing airstream. So that both in terms of sensible heat and humidity, that they give you control that aids your overall your air conditioning and heating systems. And they don't run a compressor.
I am not familiar enough with them to speak at any sort of length. I have seen some facilities that have used them to great success. I'm not sure how feasible they are at a smaller scale.
They actually, I've seen them on actually home scale systems as well. The big thing for an industry location is just that they don't tolerate dirty air, or if it's got contaminants that'll be adsorbed and then desorbed from the airstream, they're not good for that. But if you've got relatively clean airstreams, you can recover a lot of energy with a very limited energy investment. So anyway, just
Yeah, I have seen them used to great success. I haven't worked on an ethically wheel project myself, so I'm certain that the utilities would provide great incentivization for that, but don't know from my experience. But thank you. Yeah. So just going into a couple of quick projects that I've worked on over the years in terms of incentives. So for one liberal arts college, doing a number of projects which included solar thermal, solar hot water, working on their controls, and a DI as a direct installation of low flow water fixtures. We've saved them 125,000 therms a year. Over the lifespan of the projects, it'll save them over $1 million, and the utility has kicked in over $225,000 towards the cost of the projects. And then some of the hospitals, there was one hospital where you did a pipe installation job that saved them over 34,000 therms a year. The project costs $126,000, and it was such a good return on investment that the utility provided 100% of the cost of the project. And then another hospital doing a replacement of their water fixtures and a replacement of their burners on the boilers, saved them over $10,000, over $75,000 over the cost of the project, and the utility kicked in $21,000. So the incentives for some of these projects are very substantial. I know for Eversource and Liberty Gas, they're more based on the amount of savings that are produced from the project than the cost, but there are potential for significant if it's part of your capital planning project, remembering that the utilities do have great incentives for projects can free up some of that budget that's put towards O&M or capital improvement projects.
So Angel, we are actually at 3 o'clock. This has been a really interesting conversation, and you are right smack on time.
Great.
That's wonderful. Does anybody have any final questions for Angel before we let y'all go? Well, let me just say thank you so much, particularly because I know you're not feeling well today. I really appreciate the depth that you got into. I have been wanting to hear someone dive into the specifics of savings, energy conservation savings associated with equipment for years now, and this just really fit the bill for me, and I think for us, and I just cannot thank you enough for your time on this. I hope that people take down Angel's information if you want to find out more, and we will make the slides and the recording available. If anybody wants it, just reach out to me and I'll make sure I get that to you. So I think we'll just let everybody go, and thank you all so much. And again, thank you, Angel, for your time.
thanks, Angel.
Thank you, everybody.
Thank you.
Take care.
Bye-bye. All right, wait, I want to do what?